Welcome to today's webinar, Overcoming Hydrogen Simulation Challenges, brought to you by CONVERGE Science. Thank you for joining us today. My name is Mattias Sulis and I am part of the business development team at CONVERGE Science. I will be your host for today's event. We are very excited to share with you all the work we did in the space of hydrogen combustion. CONVERGE Science is a rapidly growing computational fluid dynamics software company. Our flagship product, CONVERGE, is an industry-leading CFD solver used around the globe to simulate fluid flow in complex systems. CONVERGE features truly autonomous meshing, which eliminates all user meshing time and helps provide fast, accurate results for our clients. I would like now to introduce our speaker, Dr. Samira Vijayakulasurya. Samira is a senior principal engineer at CONVERGE Science. He has been with the company for more than 11 years, leading the internal combustion engine application support team, and he is a key resource for CONVERGE support globally. Without any further delay, I will now pass the ball to Samira. Thank you all.
Thank you, Mattia. Let's get started. The outline of this webinar. This is what we are going to cover in this webinar today. There's a lot of interest globally for hydrogen to be used as a fuel in different power generation sectors. We will start from there and then look at some of the design challenges we face with hydrogen when combusted for power generation. Computational fluid dynamics, or CFD, is a key in analyzing and finding solutions to these challenges, which has become an integrated component in today's design and development processes of powertrain technologies. This would bring us to the main discussion of today's webinar, looking at how CONVERGE can be used to overcome simulation challenges associated with hydrogen combustion in various combustion devices. I will then show you some of the hydrogen combustion work done using CONVERGE that are available in public domain. These cited work should show the capabilities of CONVERGE when it comes to hydrogen combustion in devices ranging from IC engines to microturbines to rotating detonation engines. I will finally present some IC engine example cases available in CONVERGE Studio, which will be a good start to look at the model parameter recommendations for hydrogen combustion. Hydrogen combustion is quite popular these days as a means of carbon-free mobility. And I will like to talk about these two specific cases I came across recently. On the left-hand side of my screen, I show a press release from Argonne National Laboratory, where both Argonne and Oak Ridge National Laboratory have entered into a corporate research and development agreement with Wabtec, which is a leading manufacturer of freight locomotives. This agreement also includes CONVERGE Science as a software provider for in-cylinder combustion. The project will run for 4 years, during which the team will develop hardware and control strategies for the engine, which will run on hydrogen and diesel fuel to demonstrate the viability of using alternative fuels. The figure on the right-hand side of the screen shows an excerpt of the press release from Rolls-Royce. According to this press release, Rolls-Royce and EasyJet has successfully ground tested an aero engine with hydrogen produced by wind and tidal power. It marks a major step towards providing hydrogen could be a zero carbon aviation fuel for the future. According to this press release, both companies have set up to prove that hydrogen can safely and efficiently deliver power for civil aero engines, and also are already planning a second set of tests with a longer-term ambition to carry out flight tests. Hydrogen will be referred to as a fuel throughout this webinar, although, as we know, it is an energy carrier that can be produced from clean renewable energy sources, such as solar, wind, and tidal energy. One of the main advantages of hydrogen as a fuel is that it can be used readily in fuel-agnostic engines. By doing so, we can still leverage on the reliability, durability, existing supply chain, and existing engine manufacturing and recycling infrastructure. This way, hydrogen combustion engines provide a near-term, widespread solution to reduce carbon dioxide emissions from transportation sector without having to change the powertrain technology. As we know, when hydrogen is burned, you don't get carbon dioxide emissions. And if produced by renewable sources, hydrogen presents a green solution to transportation. One of the main constraints of increasing thermal efficiency in modern internal combustion engines is by increasing compression ratio or knock limits. Hydrogen has a higher octane number, and combined with its faster flame speeds, provide an ideal solution to increase thermal efficiency by reducing knock tendencies when operated at higher compression ratios. There's literature suggesting hydrogen ICEs, or internal combustion engines, can attain thermal efficiencies of around 45%. Even though hydrogen qualifies as a viable fuel to provide a near-term widespread solution to reduce carbon dioxide emissions from transportation sector, it has several noticeable challenges that engine designers should overcome. Hydrogen trapped in cylinder crevices can ignite during the valve overlap period, which poses a flame flashback risk into the intake port in dual fuel engines where a low reactivity fuel is mixed with intake air. Now, flame arresting devices should be installed in intake port to alleviate these risks. Exhaust gases also can backflow towards the intake manifold during valve overlap in hydrogen port fuel injection engines, and which can also create risk of flame backfiring. During fuel changeover of gas turbines, flashback of the flame into fuel injector at higher hydrogen concentrations can occur. Hydrogen burns hotter compared to other hydrocarbon fuels, and this can give rise to hotspots on the combustion chamber walls. This can lead to undesirable autoignition of hydrogen eventually. Design engineers should also find solutions to impact of potential higher NOx production when hydrogen burns in air because it has higher temperature, and hence the NOx will be higher. And another issue is combustion stability. Now, these combustion stability issues can arise from a wide flammability range of hydrogen, higher flame speeds, tendency to transition to detonation quickly, and smaller quenching distances of hydrogen. There are some flow-related challenges also with using hydrogen as a fuel. Direct injection of hydrogen into ICEs typically result in high-speed jets that are supersonic. And micromixes in gas turbines can result in complex unsteady flow fields that needs to be carefully assessed. CFD is an efficient and cost-effective tool available for engine designers to gain more insight into these challenges and to test viable solutions. We will now be looking at how CONVERGE can effectively be used for such analysis in the next few slides. As we mentioned in the previous slide, one of the challenges of burning hydrogen inside an internal combustion engine is a risk of flame flashback into the fuel intake manifold. One mitigation technique available is placing a flame arrestor in the intake manifold. Designing flame arrestors can be quite challenging numerically, which requires some unique features to be available in the simulation tool of your choice. A flame arrestor has a large number of channels that are quite small in their widths. CONVERGE autonomous meshing is quite useful in this scenario. The flow, combustion, and wall heat transfer within these small channels need to be modeled in order to figure out if the flame is quenched or not within the channels. CONVERGE's capability to model turbulent reacting flows with conjugate heat transfer can be quite useful to predict how the metal heats up upon interactions with the numerous backfires over many engine cycles. The video on the left shows a flame arrestor with cold walls, which arrest the flame when it is introduced in a periodic manner to simulate backfiring over consecutive engine cycles. It can be seen how CONVERGE predicts the quenching of the flame under pulsating flow, which was imposed to simulate intake manifold flow oscillations generated by opening and closing of valves. The simulation video on the right starts with relatively higher wall temperatures to reproduce a flame arrestor that got heated up due to periodic arrival of backfire flame over several minutes or even hours of engine operation. This video clearly shows how the flame is not arrested when the walls are relatively hotter. Both of these simulations are done in 3 dimensions with combustion and heat transfer to and from the metal walls between the flame arrestor channels accounted for. This demonstration clearly shows how CONVERGE can be used effectively to design flame arrestors. Now let's move on to another simulation challenge. The injection velocities of hydrogen in a direct injection engine is either sonic or supersonic. Resolving these high velocities require finer measures and smaller time steps. This can be computationally expensive in terms of memory required and runtime. CONVERGE offers several solver features like density-based solver, supersonic inflow boundary conditions, and a total energy solver to resolve these high-speed gas jets accurately. CONVERGE's adaptive mesh refinement, or AMR, can be useful in using finer measures at areas of high velocity gradients to capture shock waves and resolve field layer mixing. AMR also coartens the mesh where the gradients are low, thereby reducing the cell count. This and the ability to run the case on a large number of processes is helping to reduce memory and runtime. The video shows the direct injection of hydrogen from one of our example cases available to all of our users. Now, this slide shows how hydrogen direct injection experimental data from Sandia National Laboratories is used to validate CONVERGE simulations done at Argonne National Lab. The Sandia hydrogen direct injection data from their optical engine is publicly available for everyone to use. This simulation work was presented at the recent CONVERGE user conference by Argonne. The first column shows measured velocity data using PIV, while the second column shows the predicted velocity from CONVERGE. The third column depicts measured hydrogen concentrations using PLIF, while the fourth column shows predicted hydrogen mole fractions using CONVERGE. As you move down the rows, the time is advanced. These comparisons clearly show how well the in-cylinder motion and jet wall interaction are resolved during the compression stroke by using CONVERGE. The jet impingement time, the jet penetration along the wall, and the perpendicular to the wall penetration, the roll-up of the vortex after interacting with the pistons are all predicted very accurately in this simulation. The Argonne researchers also discussed the solver and grid setup recommendations from CONVERGE in their original presentation. With supersonic gas injections comes the challenge of handling shock waves and gas expansion accurately. The top figure shows shock wave generated when endodecane liquid is injected into nitrogen. This data is from Sandia National Labs. The figure below shows how CONVERGE is used to predict those shock waves accurately. This was one of the few fuel injection related validation results available, which included a fuel injector as well as shock waves in the open literature, even though this is neither hydrogen nor gas injection, but it shows the CONVERGE capabilities. CONVERGE has all the important features necessary to capture shock waves accurately, which is going to be beneficial when simulating hydrogen direct injection. The density-based solver and the ability to specify species-based critical conditions is important when resolving density accurately in high-speed compressible flows. AMR is uniquely helpful to capture shock fronts with minimal computational expense. CONVERGE has been used to capture shock waves in different applications, and I'm listing some of them on the slide, which are available in open literature. Now let's move on to overcoming some of the simulation challenges that we face in gas turbines. Designing micromixers in gas turbines can offer some simulation challenges in that the mesh sizes necessary to resolve flow through microchannels can be quite small, and the time steps required to resolve these flows can be quite small as well. Both finer meshes and small time steps add to more memory requirement and larger simulation runtimes. Use of LES turbulence models can be quite beneficial when simulating micromixer flows in gas turbines. CONVERGE allows you to choose from several different LES models that are 0 equation, 1 equation, or 2 equations. With hydrogen as the fuel, the use of preferential species diffusion is also quite important. CONVERGE allows you to use a mixture average diffusion model to account for preferential species diffusion. The figure shown on this slide shows a comparison of measured and predicted flame length using LES and RANS as turbulence models. And detailed chemistry combustion is being used. For both simulations, mixture average diffusion model is activated. But you can clearly see how preferential molecular species diffusion is more important in well-resolved LES simulations, where the modeled turbulent viscosities are lower compared to RANS turbulent viscosities. AMR and superior scalability also can help running these large cell count cases to reduce simulation runtimes. It's a well-known fact that hydrogen has high flame speeds compared to conventional hydrocarbon fuels. Predicting different combustion-related phenomena like ignition, flame propagation, extinction, and lean blowout using hydrogen requires accurate detailed chemistry modeling and accurate detailed chemistry mechanisms, and using finer computational measures and smaller time steps. All of this results in increased computational cost. In previous slides, we have seen how AMR and access to different turbulence models turbulence modeling options can benefit combustion simulations with hydrogen. In this slide, I want to talk specifically about how CONVERGE detailed chemistry modeling can benefit your hydrogen combustion simulations. With CONVERGE, you have access to chemistry of many different fuel components, including hydrogen. As you can see in this figure, you can easily select fuel components to get multi-fuel chemistry mechanisms with CONVERGE. These mechanisms are generated and validated under the Computational Chemistry Consortium, which I will be talking about in the next slide. CONVERGE also has a thickened flame model that can be used with coarse LES simulations, which will help in reducing simulation runtime while maintaining simulation accuracy. Now let's look at the Computational Chemistry Consortium. Convergent Science founded the C3 Consortium, which perform fundamental chemistry research to generate accurate chemistry mechanisms for fuel and emission components that are of interest to its members. The mechanisms are validated against available flame speed, ignition delay, and speciation data. The large parent mechanism is already published and available for every one of you to use. CONVERGE offers several chemistry tools to generate fuel surrogates based on actual fuel specifications, extract sub-mechanisms from the parent C3 mechanism, reduce them further with ignition delay and laminar flame speed targets, merging and optimizing these mechanisms. These tools are available to all CONVERGE users without any additional licensing cost. The C3 parent mechanism has been validated extensively using combustion vessel and engine data. I invite you to read the publication that is shown on the slide to learn more about these validations. Convergent Science is working with several partners in the industry, academia, and national labs throughout the world to bring you the latest cutting-edge fuel chemistry mechanisms through this consortium. In detailed chemistry for hydrogen combustion is relatively inexpensive compared to popular hydrocarbon fuels, in that the number of species and reactions are small. Another positive fact is that there are a lot of hydrogen chemistry mechanisms available in the open literature. I'm listing some of these available mechanisms for those of you who are interested in this slide. With CONVERGE, you can use any of these mechanisms or extract hydrogen chemistry from the parent C3 mechanism as shown in the figure here. Before using any chemistry mechanism, it is recommended to understand the range of operating conditions for which the mechanism has been validated. The validity ranges for hydrogen chemistry that can be extracted from the C3 parent mechanism is given on this slide. In a previous slide, I stated that it is important to use preferential species diffusion for micromixers in gas turbines when well-resolved LES turbulence modeling is used. This is also true for most other applications that rely on accurate molecular mixing rates and laminar flame speeds. The figure on the right shows laminar flame speeds of hydrogen at 1 bar as a function of premixing ratio. The open symbols are the data available in the literature. The solid lines are CONVERGE simulations using mixed average diffusion model, while the dashed lines are CONVERGE simulations using single species diffusion model. The red lines correspond to 3D simulations, while the blue lines corresponds to 1D simulations. It can be clearly seen that accounting for preferential mass diffusion through the mixed average diffusion model is quite important in predicting the correct hydrogen laminar flame speeds. Some of the hydrogen engines operate in dual fuel mode, and let's look at some of the challenges we face there. In order to do this, you need combustion models that can work or account for dual fuel. CONVERGE detailed chemistry solver can be used to simulate multi-fuel combustion very easily. You just need a chemistry mechanism that includes chemistry for all the fuels of interest. As we saw before, you can easily extract multi-fuel chemistry mechanisms from the parent C3 mechanism. The video you see on slide depicts the premixed combustion of ammonia and hydrogen using extracted chemistry from the parent C3 mechanism. So this mechanism includes both ammonia chemistry as well as hydrogen chemistry. With hydrogen burning hotter, one of the concerns to engine designers is higher NOx emissions or nitrogen oxide emissions. There are several methods that can be used to NOx reduction, such as lean burn, use of EGR, and water injection. Most of these strategies require accurate numerical simulations that resolves gas mixing, liquid spray, evaporation of that liquid spray, and combustion as well. Our clients have been successfully using CONVERGE for all of these applications for many, many years. With CONVERGE, you can simulate the engine out NOx production with several different models available for you, and also predict after treatment methods of NOx reduction in the exhaust. One of the final simulation challenges I want to touch upon is a trivial one, but an important one. With so much research and development happening in hydrogen combustion modeling field, how do you make sure that you have access to the latest cutting-edge technologies at all times? As with the solution to other challenges we looked at today, the answer lies with CONVERGE. We are working with leaders of hydrogen combustion research from various industrial and academic institutions. By using CONVERGE, you will get access to all of that collaborative knowledge. Convergent Science regularly holds application-specific workshops and conferences where sessions are dedicated to emerging and popular technologies. This past summer, we held an application workshop in Torino, Italy, dedicated to hydrogen. Our clients and partners presented on the hydrogen combustion modeling work they are doing with CONVERGE during our recent user conference in Madison, Wisconsin this past September. I have posted 2 of these presentations on these slides for your reference. Now we move on to the final part of our webinar, where we get to see some of the validation work on hydrogen combustion using CONVERGE. Convergent Science has conducted fundamental validation work on hydrogen combustion like laminar flame speed, quenching distance, and maximum experimental safe gap. Due to the time restrictions, I'm not going to show these today, but they are available for you to download from our website with our hydrogen combustion training slides. I chose to show some application-specific validation work to you today. They range from ICE engines to micro gas turbines to rotating detonation engines. The first validation work we are going to look at today is of ICE engine combustion. We got this case from CMT Motors. The engine was run with port fuel injection and direct injection of hydrogen. And we are only going to look at the port fuel injection validation part today. The hydrogen injector can be seen in the intake port on the top figure. The simulations were first run with a premixed assumption at the inflow boundary, as shown on the bottom figure. The port fuel injection simulations were run next. Simulations were run for 5 operating points, which spanned different load points and equivalence ratio cases. Detailed chemistry solver was used to model hydrogen combustion, and we tested 2 available mechanisms, as can be seen on the screen. Rand's turbulence modeling was used with mixture bridge diffusion model to account for preferential species diffusion. 62.5 micron cell sizes were used to resolve the initial spark kernel growth, and then 0.25 millimeter cell sizes were used to resolve propagating hydrogen flame front using temperature IMMA. The maximum total cell count for this simulation was around 3 million. Here are some of the results that we see with premixed hydrogen inflow boundary condition. The top left is the low load case, and the bottom right is the high load case. The other 3 cases are mid load cases with different equivalence ratios. There are 250 consecutive experimental cylinder pressure cycles that you see in gray, and converged simulations are in green and blue. The different colors correspond to different chemical mechanisms used, and there are 5 consecutive engine cycles run for each of those mechanisms. No model parameters are tuned from case to case. The simulation results lie within experimental data ranges, which makes them valid and accurate realizations. Since both since both chemical mechanisms provided accurate results for the premixed case, we decided to use the C3 mechanism for the PFI simulations and going forward. From left to right, they are the low load case, one of the mid load cases, and the high load case. There are 5 consecutive cycles run for the simulations without any model parameter change between cases. You can see that the predictions are within the cyclic variation of measured data. I also want to bring up a testimonial from Dr. Amar Avdik from Daimler Trucks. Dr. Avdik delivered one of our keynote speeches at the recent CONVERGE user conference and discussed how they have been successful in using CONVERGE for their hydrogen combustion simulations for both port fuel injection and direct injection engines. Now, let's move on to some of the validation work in gas turbines. The following work show how LES and detailed chemistry modeling in CONVERGE have been used successfully to predict the flame flashback into the fuel injector at higher hydrogen substitution rates. The paper compares the predictions with experimental results to validate that CONVERGE can predict this phenomena accurately. The following work done at Purdue University shows how CONVERGE has been successfully used to predict lean blowout of 2 different fuels, methane and hydrogen, in a gas turbine combustor. The simulations were able to run and predict the different lean blowout temperatures as shown in the video. Now, in one of the previous slides, we discussed how we at Convergent Science collaborate with experts in the industry to bring out cutting-edge research on hydrogen combustion, and how we are always sharing that with you. This validation of a rotating detonation engine is one such example. In this work between Purdue University and Convergent Science, it is shown that accurate mode transition can be predicted with CONVERGE. The simulations were able to accurately capture the number of shock waves, and the shock wave frequencies when transition happened between the 2 cases. This numerical work of predicting deflagration to detonation transition of hydrogen, This numerical work of predicting deflagration and detonation transition of hydrogen flame clearly depicts the advantage of using innovative features of CONVERGE. AMR based on temperature and pressure can be seen to capture the propagating shock wave and the flame front on the bottom figure. So you can see how the flame is propagating over the obstacles and quickly transitions on to a detonation front. In fact, this is hydrogen air mixture transitions to detonations in a 25% blockage ratio in an obstructed channel. The final validation I want to show you is of a microturbine. So CONVERGE can also be used to model microturbines that are fueled with hydrogen. This work on high hydrogen blends combustion in microturbine combustors was presented at the recent CONVERGE user conference by researchers from Argonne National Laboratories. Finally, I want to show you two hydrogen IC engine related example cases available in Studio for you to use readily. One is using detailed chemistry, while the other one is using a combustion model called ECFM. Now, you can use CONVERGE chemistry tools to generate ignition delay tables and laminar flame speed tables from detailed chemistry mechanisms and use them with combustion models like ECFM and G equation when simulating hydrogen combustion. So I invite you to use these example cases to look at the preferred settings that we have set it up with, which would be a great starting point for your simulations. Now that's all I have for you today. And before we open up the sessions for questions, let us quickly summarize what we discussed so far. We talked about the various simulation challenges faced by engineers who want to model hydrogen combustion. First, higher computational costs have to be incurred due to some extreme conditions and properties of hydrogen. Then, in order to simulate hydrogen combustion accurately, we require some specialized models and capabilities to be available in the numerical tool that you are going to use for hydrogen combustion problem. Then we looked at in detail how CONVERGE offers a tool to accurately simulate different hydrogen combustion phenomena. CONVERGE includes all the required models and capabilities that are needed for you to simulate hydrogen combustion accurately and to overcome most of the simulation challenges you might face while doing so. With that, I invite you to try CONVERGE to simulate your hydrogen combustion problem.